We're going to finish up the constant velocity worksheets with problems 9 and 10. These are a little bit misnumbered. This should be number 9 instead of number 8. But that's all right. The answers are still correct. So number 9, a bicyclist makes a trip that consists of 3 parts, each in the same direction, which is due north, along a straight road. During the first part, she rides for 22 minutes at an average speed of 7.2 meters per second. We're just going to take a look at each part individually. So for part 1, the velocity was 7.2 meters per second, and the time was 22 minutes. We don't do anything in minutes, we do seconds. So 22 minutes is 1,320 seconds. You have to multiply 22 by 60. Now for the next part, she rides 36 minutes at an average speed of 5.1 meters per second. So the velocity is 5.1 meters per second, and when we convert the time to seconds, we get 2,160 seconds. And finally, part 3, the person rides for 8 minutes at an average speed of 13 meters per second. So there's the velocity, 13 meters per second, and the time is 480 seconds when we convert it. The question A, how far has the bicyclist traveled during the entire trip? B, what is the average velocity for the entire trip? So the first part's very easy, the total displacement, total distance. They can be used interchangeably in this one because they've only gone in one direction. And that's going to be D equals velocity multiplied by time. We just have to do that for each part. So we take part 1 velocity multiplied by part 1 time for 9,504 meters. We do the same thing in part 2, velocity multiplied by time gets us 11,016 meters, and the same thing now for part 3 gets us 6,240 meters. So the total distance traveled is 26,760 meters. So that's the total displacement or distance traveled by the bicyclist. Now we're looking for average velocity. Average is not calculated like you would do it in math class, where you would add together 7.2 and 5.1 and 13 and divide by 3, because you traveled each of these velocities for a different amount of time. So we can't just add them together. We traveled 5.1 meters per second a lot longer than we traveled 13 meters per second, so we can't just add them together and divide by 2. In order to find the total average velocity, we need to do the total distance over the total time. The total distance we just solved, 26,760 meters. The total time, or all 3 of the times added up, so the 1,320, 2,160, and 480. Add all those together, and you get 3,960 seconds. Divide these two things together, and we get an average speed of 6.76 meters per second for the trip. Last one, number 10. 2 cars are being collided for an episode of Mythbusters. The 2 cars will be placed 80 meters apart. You can see the 80 meters there. And they're going to travel at different speeds. The car on the left, we'll call that the blue car, is 13 meters per second. The car on the right is going to travel 8 meters per second. Notice the little negative right there. That's because it's going to the left. How far from the blue car will the 2 cars collide? Well, I've got blue car stuff and I've got red car stuff. I do not have a displacement or a D for either one. By the way, displacement is very, very, very important here. We're not talking about total distance. We're talking about displacement, and more accurately, we're talking about the position, where these things are going to be located from a starting point, which is where the blue car is located. The velocity of the blue car is 13 meters per second. Velocity of the red car, negative 8 meters per second. We have our equation, which is D equals velocity multiplied by time. Now over here, we have D for the red car equals velocity multiplied by time. We want to know when these two D's will be the same, when they will be at the exact same spot on this particular point, like on this little line here. Well, I had to add 80 meters. Now, there's a little explanation here. The reason for the 80 meters is, if you were thinking about this like a race, let's say they were both going to the right. This car has an 80-meter head start. It's 80 meters ahead of the blue car. So if we're saying that the blue car is starting at 0, that's our 0 point. The red car is not starting at 0. It's starting at 80. But we have to factor that in because D is where it's located. D is where is this thing in space? Well, at time 0, when T is nothing, where was the red car starting? The red car started at 80 meters. So this 80 meters, all that's doing is just saying, the D is really just saying, where is this thing? From some starting location. Well, we're going to say that the starting location, the 0 point, is where the blue car is. So at time 0, the red car is not located here. It's located out here at 80 meters. So when time is 0, for the red car, D equals 80. So at time 0, V times 0, this whole thing would go away. d equals 80. That's why this works. Now that we've done that, I'm looking for when the two d's are the same, when they hit each other, so they're both going to be located at the exact same spot. So the d for the blue car and the d for the red car is the same. It's not how far they've gone, it's not the distance traveled. Remember, this is displacement. That's where sometimes the difference is very, very important. This is one of those times. So because these two d's are the same, we want to know when they're going to be at the exact same spot. I know that the equations, vb times t, so velocity of the blue car times time, and velocity of the red car multiplied by time plus 80, those two things have to be equal to each other because they're both equal to the same d. So velocity of the blue car multiplied by time, I just brought that down and left it on the left side of the equation. And then this stuff over here, the velocity of the red car multiplied by time plus 80, is on the right side of the equation. I'm solving for time. This is a whole lot like what we did here in number 5 when we were, number 8 when we were solving for the bear and the guy. Now they're just going in opposite directions, but we're still solving for the time. We're going to put these two things together as a simultaneous equation, and we're going to solve for time very similarly. So I've got a term with time in it on the left side of my equal sign and a term with time in it on the right side of the equal sign. I have to get those together, so I'm going to subtract velocity of the red car and time over to the left. So now on the left side of the equation, I've got velocity of the blue car multiplied by time minus velocity of the red car multiplied by time, and on the right side, I've got 80 meters. I factor out my time, leaving me with velocity of the blue minus velocity of the red in parentheses equals 80 meters. And now I'm going to divide these two velocities over to the right side. That's what happened here. Sorry, it got a little messed up going through the scanner, but you can still see it. 80 meters divided by 13 meters per second for the blue minus negative 8 meters per second. You have to make sure you have that negative sign, or you get a very weird answer. And that's going to give us a time that they will hit in 3.81 seconds. After they go, about 3.81 seconds until they hit each other. Plug that time into either one of the first equations. I did it for the blue car. D equals velocity of the blue car multiplied by time. Velocity of the blue car was 13. Time was 3.81 seconds. Multiply the two together, and you find out they're going to hit 49.5 meters away from the blue car.